What?
Did you start Tuesday, Richmond?
Well, the selection Sunday is Sunday. But I think games start Tuesday.
I'm running.
We scheduled my calc.
Look,
Look, you smiled.
I am, so I think you too.
I'm excited.
It's such a good movie.
I'm going to see the first game on Tuesday.
I gotta drive here.
And at first
I've never driven.
back here, driven like everywhere.
I know my mom just said we like to drive in the morning. I gotta drive when there's lots of cars out on
Freaking 20 minutes.
Did you have a question?
No, I was saying I gotta drive here.
Everybody
So
stay off the
you
road.
was
So raise your hand.
Alice driving.
I
Yeah,
was not driving.
stay up the
I did.
sidewalk.
I really don't want to get
I live in a freeway. Olivia's head is in my.
Like me.
I don't want to go back.
I'll be like at college, we'll still have to drive with my mom. Actually, I can drive with my sister.
No, you won't. You can
College starts beginning of August. Or end of
Oh, yeah.
August.
And you have to
And I can't get
What?
my license until September.
Wait, what time are we done today?
I'm so happy.
Like,
And then I can get home from work early, and then I can reach my days drop by me. And then I can just,
Yes, that's what you like spring it up.
What?
Don't
What's
stay
today?
back to work. I'd say that here.
It's gonna be fun.
Okay, so to get back to where we were at the end of last class, let's remind ourselves of a couple of facts. One, the hydrogen ion concentration is able to be expressed as 10 to the negative pH power. So whatever your pH is an expression of your hydrogen ion concentration. I think that makes sense because when you look at the pH scale between 0 and 14, between acid and base, what makes an acid is the fact that it has lots of hydrogen ions. What makes a base, the fact that it has very few hydrogen ions. So when you look at your hydrogen ion concentration, that is an expression of pH. Just as well, your hydroxide ion concentration is also an expression of pH. If you take this equation and rearrange it, it can be written as pH is the negative log of the hydrogen ion concentration. If you want to know the pH given the hydrogen ion concentration, you can always use this formula. And something else that was not mentioned yesterday but needs to be mentioned is the fact that the hydrogen ion concentration times the hydroxide ion concentration is always, let me make sure I get this right, is always 10 to the negative 14th power. I want to double check that this is correct, but give me 1 second. Is always 10 to the negative 14th. These are 3 mathematical facts about pH. Hydrogen ion concentration is 10 to the negative pH power. pH is the negative log of the hydrogen ion concentration. And the hydrogen ion concentration times the hydroxide ion concentration is always 10 to the negative 14. Holly, what was your question?
Why do you put a log in there? Is it just because?
Don't beat yourself up over that. It's a mathematical expression that you haven't encountered yet. Don't even worry about the math of it. So this is a case where I'm giving you the math on faith, and you just trust me. It's in the book, so you can trust the book too. So you, Holly, and Lauren, who haven't been through advanced math, are taking this on faith. It is what it is. Just leave it at that. So here's an example I think maybe we did this one yesterday, where we said calculate the pH of a 0.0001 molar HNO3 solution. Is this what we did yesterday? Just to remind ourselves how we go through this process. If we have an HNO3 solution, when we drop the HNO3, the hydrogen nitrate, into water, the HNO3 is going to break into a hydrogen ion and a nitrate ion. Notice the coefficients are all 1. And that means that if we had a 0.0001 molar HNO3, we're going to have 0.0001 molar of hydrogen ions, as well as 0.001 molar of NO3s. In other words, the hydrogen ion concentration is 0.001 molar. And if you know the hydrogen ion concentration, you can figure out the pH, because the pH is always the negative log of the hydrogen ion concentration, which in this case is the negative log of 0.0001. So I'll go to my calculator just to make sure we got this right.
You said it was -4.
I think the log comes out to be -4, yeah. And then with the negative in front, the pH will end up being expressed positively. Because we know the pH has to be between 0 and 14. So 0.0001, going to take the log of that, get -4. So it's -4, which is 4. If you were super swift with your math, you might have noticed that 0.0001 is 10 to the -4th power. If you were really swift, you would have seen that. And if you would have, then the answer is here, 10 to the negative pH power is the hydrogen ion concentration. But that's certainly not necessary to know. Now, in light of the third fact that I have written down there, we can answer another question. We could ask, what is the concentration of hydroxide ions in this solution? Well, we know the concentration of hydrogen ions, and if we know the concentration of hydrogen ions, we can always figure out the concentration of hydroxide ions, because we know that 2 have to multiply to 10 to the -14. So we know the hydrogen ion concentration is 0.0001, and we know that the hydrogen ion concentration times the hydroxide ion concentration is always 10 to the -14. Plug in for your hydrogen ion concentration, 0.0001. And then solve for your hydroxide ion concentration. This is just algebra. 10 to the -14th over 0.0001. And then we can solve it out. Now, if you're wondering how to put 10 to the -14th in your calculator, there are 2 ways to do it. One way is to write the number 10. There's a button on your calculator that's called a caret, that is like an arrow pointing up. That's basically telling you to put whatever follows in the exponent, and then you could write -14, and that would do it. That's one way. Another way is to think of 10 to the -14 as a number in scientific notation. It's like 1 times 10 to the -14. And you could write this then 1. There's a button that has a double E on it for exponent, I believe, but I'm not exactly sure what the second E stands for. it's got 2 e's on it, though it should, on your calculator. And if you do 1 EE negative 14, your calculator interprets that as 1 times 10 to the negative 14. So that is another option. So however you manage to pull it off, I'm going to use the double E button myself. 1 double E negative 14 divided by 0.0001. Now, my calculator outputs that to me as 1 E negative 10. Now, we're going to have to reverse interpret that. 1 E negative 10 is 1 times 10 to the negative 10. So anytime you see this E to the negative 10, that's telling you the exponent on your power of 10. When you see a negative number down here, that's a really, really tiny value. So 1 times anything is just that anything. And the answer is 10 to the negative 10.
I think I got like 1 and 32 maybe.
Did you divide by 0.001? Did that do it? Good. Okay. Okay, something that is commonly done with acids and bases is, say you make an acidic solution, you run an experiment with that acid, and now you want to dispose of the acid. You're not going to just pour it down the drain, because depending on what the acid is, it could be corrosive enough to eat through something that's in the drain and then cause all sorts of plumbing issues. So what you would do is you would want to take something that was acidic that you're disposing of, mix it with a base in order to make it neutral, like water, and then pour it down the drain. Seem reasonable? Okay, this process is called titration. I'm not exactly sure why. But titration is basically the process of neutralizing an acid with a base, or vice versa. When I say vice versa, you would either neutralize an acid with a base or a base with an acid. But when we talk about neutralizing something, we're talking about taking something that has a pH not equal to 7 and bring it to a pH equal to 7. So that there's no acidic properties, no corrosive properties, pour it right down the drain. Now, the way to make sure that you're neutral, think about this. Neutral, to be pH neutral, means that your hydrogen ion concentration equals your hydroxide ion concentration. Remember, the definition of neutral is water. And water is the substance that has a perfect balance between hydrogen ions and hydroxide. So anytime you're doing a titration, if you have an acid, what you need to figure out is how many hydrogen ions you have. So then you can make sure that with your base you have just that many hydroxide ions and you'll cancel out. So let me give you an example. Milliliters of 0.01 molar HCl is neutralized via titration with 15 milliliters of an NaOH solution. sodium hydroxide. The question is, what is the molarity of the NaOH solution? If you have 10 milliliters of a 0.01 molar HCl solution, you have 10 milliliters of acid. That means that there's a certain number of hydrogen ions in that HCl. Let's look at this in two cases. One is our acid, and one is our base. Let's go into our acid solution and figure out exactly how many hydrogen ions we have. Because if we know how many hydrogen ions we have, and we know that the two solutions neutralized each other, we know that the basic solution had just as many hydroxide ions. And then we can use that fact to figure out exactly what the molarity of the sodium hydroxide is. So, first, let's look at the equation. HCl, when dropped in water, will break into a hydrogen ion and a chlorine ion. A chloride ion, I should say. Notice the coefficients are 1 in every case. So if we have a 0.01 molar HCl, we have 0.01 molar hydrogen ions and 0.01 molar chlorine ions. Well, right there you have the hydrogen ion concentration. 0.01 molar. Now, the fact that the hydrogen ion concentration is 0.01 molar does not tell us exactly how many hydrogen ions we have. We're going to have to use the 10 milliliter fact in order to do that. So let's set up our molarity equation. Molarity equals moles of solute over liters of solution. The molarity of hydrogen ions is 0.01. The moles of solute, I have no idea, but we do know how many liters are in our solution. If we have 10 milliliters, hop the decimal 3 to the left, we have 0.01 liters of solution. That can be solved out. So the moles of solute, in this case, we're looking at the moles of hydrogen ions. We can solve out here, do the cross multiplication. It's basically 0.01 times 0.01. The moles of hydrogen ions come out to be 0.01 times 0.01. That's 0.0001. Now that tells you how many hydrogen ions are in our acid. Which means, if there's this many hydrogen ions in our acid, the moles of hydroxide ions coming from our base has to be exactly the same. Because however many hydrogen ions I have to have that many hydroxide ions to neutralize. You could almost think of it like, say you're making a sandwich or something and you have a particular number of slices of bread and a particular number of slices of meat. Right, let's say you put 2 slices of meat for every 2 slices of bread. Well, you're going to have then, if you have this much bread, you're going to have that much meat to mix with it. It's kind of that idea. You're taking 2 things that go together, and you're going to have equal amounts of both if you're going to neutralize. But now, we know how many moles of hydroxide ions we have. We know how many milliliters of that solution. So we have moles of solute as well as liters of solution. We can work backwards with the molarity equation to figure out what the molarity of the sodium hydroxide must be. So, set up the molarity equation. Moles of solute over liters of solution. Here, with the base, we're talking about the molarity of the hydroxide ions. which we don't know yet. But what we do know is the moles of solute is 0.0001, and we know the liters of solution in the case of the base, we had 15 milliliters, so hop that decimal 3 to the left, we have 0.015 liters. We do the division there, and we get 0.00667. Now, what is that telling us the molarity of? That's telling us the molarity of the hydroxide ions. Let's work backwards to figure out the molarity of the sodium hydroxide solution. What's going to happen to the sodium hydroxide when we drop it in water? It will dissociate into sodium and hydroxide. Notice the coefficients here are all 1. That's really nice to work with. Now we did, with our computation, figure out that the molarity of the hydroxide ions is 0.00667, which means, since all of these coefficients are 1, that the sodium ion concentration is 0.00667, and the NaOH concentration is also 0.00667 molar. And there's our answer. The key to solving the problem is right here, when you bridge the gap from the acid to the base by saying, if we neutralized, we have to have exactly as many hydrogen ions as we have hydroxide ions. Because if we had fewer hydroxide ions, then we wouldn't have enough hydroxide ions to pair up with all of the hydrogen ions. We would have extra hydrogen ions and our solution would still be acidic. If we had too many hydroxide ions, the hydroxide ions would pair up with all of the hydrogen ions, but then we would still have extra hydroxide ions, and now our solution is basic. That doesn't solve the problem either. So in order to solve the problem, we have to have as many acid particles as we have base particles, so that whenever they combine, they completely neutralize each other. Does anybody have a watch on? What time is it?
It's
8:50. Okay. Thanks.
That's like,
A 15.5 milliliter sample of 0.215 molar potassium hydroxide is required to neutralize 21.2 milliliters of acetic acid via titration. Calculate. The molarity of the acetic acid. .5 milliliter sample of 0.215 molar potassium hydroxide. So immediately you read that first bit, you know you have a sample of base. You see the hydroxide ions. And it's being neutralized, or it is neutralizing acetic acid. So let's take a look here. Two cases. Our acid and our base. Now our base, we know, is potassium hydroxide. I could even write the equation up here to start. What would happen with our potassium hydroxide when dropped in water? Well, it would break into a potassium ion and a hydroxide ion. Notice coefficients are 1 in every case. That's going to be nice. That's going to be easy to work with. Because right off the bat, shoot, we can keep filling in information here. Potassium hydroxide has a molarity of 0.215, so everything in this equation, because the coefficients are 1, has a molarity of 0.215. If we had a coefficient of 2, we'd have to multiply by 2, and a coefficient of 3, we'd have to multiply by 3, because what would start as 1 particle would break into 3 particles, and thus have 3 times the concentration. Now, if we go to our acid, acetic acid, we're going to have to know what that is. So, acetic acid. Go back to your naming conventions. Notice there's no hydro in the name, so this is dealing with a polyatomic ion. Acetate, good. So, when you see acetic, the suffix IC corresponds to the suffix ATE on your polyatomic ion. Does anybody remember what an acetate ion is? C2H3O2 minus. It looks right when you see it. If that wasn't obvious, I put the page on the board the other day of what page to go back to on the book to remind yourself of that. And now if you're going to make an acid out of this, you're going to have to bond this to hydrogen, and you can see how that comes together. So you have HC2H3O2, and when you drop that into water, you're going to break apart into a hydrogen ion and an acetate ion. Notice what was 1 particle to begin with breaks into 2 particles, each of which there are 1 of. So with 1s as coefficients, that works really nicely, because whatever the molarity of our hydrogen ions is also going to be the molarity of our acetate. So in this case, unlike the last problem where we had to start with the acid because we knew more about it, in this case we know more about our base. We're going to have to work with our base and then say, okay, how many hydroxide ions do we have? We're going to have just that many hydrogen ions. So let's figure how many hydroxide ions. That's really the question, is how many OH minus ions do we have? That's an important question because once we know how many OH ions we have, we just need to have that many H ions, and the 2 are going to come together and make water. Well, let's use our molarity equation. Molarity equals moles of solute over liters of solution. We're looking at the molarity of the hydroxide ions, so we're going to take 0.215 molar. The moles of solute is what we want to answer. To answer a question of how many, we need a quantity unit, and our quantity unit is moles. The liters of solution, hop the decimal 3 times, is 0.0155. So once I multiply this together, I guess we'll have to stop. The moles of solute, which are, in this case, moles of OH ions, that's what we're looking at, is 0.215 times 0.0155. That comes out to 0.0033325. And if there's that many hydroxide ions, the thing that we know must be true is the moles of hydrogen ion better be the exact same, or else they're not going to neutralize. This fact will allow us to solve the problem, which we'll have to wait until Monday to do. So next week sometime, probably Thursday or Friday, we'll have a test in here over acids and bases. We're getting to the point where we can do lots of problems with them, and I'll probably do this on Monday to get you guys ready for the test.